1940. London, United Kingdom. Britain was entering its second year of war. Resources were stretched thin, industries were converting to military use, and every branch of government faced the same question: how can we keep the country functioning under total war? At the center of that challenge was an engineer named Sir William Henry Glanville. Few outside the scientific community knew his name, yet almost every military vehicle, airfield, and supply route depended on his work. Glanville was a civil and research engineer. Before the war, he led the Road Research Laboratory, studying materials, traffic flow, and bridge safety. But when war began, his laboratory's role changed overnight. Instead of studying peacetime transport, it became a key arm of Britain's defence network. The War Office called for a new mission: to make Britain's roads, runways and shelters resistant to war. Glanville accepted without hesitation. His team of civilian engineers was reassigned to military research, and their first task came immediately: strengthening the country's airfields. Heavy bombers, like the Wellington and later the Lancaster, demanded stronger surfaces. Britain's early air bases had been built quickly, often on farmland that softened after rain. Aircraft were skidding, sinking, and damaging landing gear. The Royal Air Force needed a solution that could be produced fast, with limited materials, and used across hundreds of locations. Under Glanville's direction, the Road Research Laboratory began a series of tests that blended pure science with field engineering. They analyzed soil composition, loading weights, and the effects of repeated aircraft landings. Out of that research came a new standard for airfield construction: a layered foundation system using compacted materials and reinforced concrete. It was designed to carry the heaviest aircraft Britain could produce. Within months, the new method was applied nationwide. Airfields that once failed after weeks now lasted through entire campaigns. The change was immediate and measurable. Fewer aircraft lost to runway damage, faster repair cycles, and improved sortie rates. Once the airfields were stabilized, Glanville's focus shifted to road durability. Military transport vehicles were heavier and more numerous than anything Britain's road network had faced before. Ordinary tarmac surfaces cracked under the strain. The laboratory developed stronger binding materials using crushed rock and bitumen mixtures tested under simulated tank movement. These formulas later became standard for Allied supply routes across Europe. At the same time, Glanville's team investigated the effects of explosions on concrete and steel. Their studies helped design blast-resistant structures, from factory walls to public shelters. Civil defense authorities quietly relied on his data to protect workers and civilians. What made Glanville's contribution so effective was his approach: fast testing, direct communication, and immediate implementation. He cut through bureaucracy, treated every experiment as a field operation, and delivered results the military could use within weeks. By 1941, his laboratory was operating as an unofficial technical branch of Britain's war effort. Reports from his engineers informed nearly every decision about airfield expansion, bridge construction, and protective building design. For the public, his name meant little. For Britain's engineers and planners, it meant reliability. Whenever a structure was marked RRL approved, it meant it would hold. And as the war expanded toward North Africa and later Europe, the methods Glanville established in those early years would become vital to the largest military construction projects of the entire conflict. 1941. Britain's war machine had settled into a pattern of endurance. Production lines were stable, but transport was reaching its limits. Tanks, supply trucks, and bomber convoys were wearing out Britain's roads faster than they could be repaired. The question confronting the War Office was no longer just about weapons or manpower. It was about infrastructure survival under continuous strain. At the center of that problem stood the Road Research Laboratory, led by Sir William Henry Glanville. What began as a small group of civilian engineers was now operating under military secrecy, reporting directly to the Ministry of Supply. The laboratory's work was classified because its results determined how fast Britain could move fuel, food and ammunition across the country, and later across Europe. Glanville's team approached war engineering with the same precision they had once used for civil research. But the objectives were now urgent and tactical. Each project started with a single measurable question. How much weight can the system carry before it fails? Their first focus, after the airfield successes, was bridges. The British Army was preparing for offensive operations overseas, and it needed bridging systems that could be built quickly and hold unprecedented loads. Pre-war bridge design assumed lorries weighing under 10 tons. By 1942, a single Churchill tank weighed over 40. Existing structures would collapse under that pressure. The laboratory's testing program was relentless. Engineers constructed full-scale bridge sections, loaded them with tanks, and recorded stress points using strain gauges and photographic methods. The data revealed that many standard military bridges were over-engineered in some areas and dangerously weak in others. Glanville's team introduced modular reinforcement principles, a system of detachable steel panels that could be strengthened on site depending on expected vehicle weight. These findings directly influenced the development of the Bailey Bridge, designed by Donald Bailey of the Royal Engineers, but validated and refined through testing at Glanville's facility. The Bailey Bridge would become one of the most successful engineering achievements of the entire war, allowing Allied forces to cross rivers and ravines within hours. While bridges were being tested, another division at the laboratory studied the effect of repeated heavy vehicle traffic on different road compositions. Wartime traffic density had multiplied several fold since 1939. Civilian asphalt surfaces cracked under sustained use, creating potholes that slowed convoys and damaged tires. Glanville's researchers compared mixtures of crushed rock, bitumen, and synthetic binders to determine which combination offered the best resilience under constant mechanical stress. From this came a new wartime standard for road surfacing, a dense bituminous macadam that offered both flexibility and strength. It reduced maintenance cycles by half and became the template for military road networks built later in France, Belgium, and the Netherlands after D-Day. Parallel to these mobility studies, Glanville opened a collaboration with the Building Research Station to study blast effects on structural materials. Britain's cities had endured thousands of air raids, yet few scientific tests had been conducted under controlled conditions. His team built small-scale reinforced concrete frames, detonated explosives nearby, and recorded how shock waves moved through walls, columns, and floors. The resulting data informed the design of air raid shelters, ammunition depots, and military factories. It allowed architects to calculate safe distances between walls and supports, reducing collapse rates during subsequent raids. These principles later evolved into post-war building codes for blast-resistant construction. Glanville's management style was methodical and impersonal, but it was extremely effective. He insisted that each test produce immediate, actionable results. Reports were concise, tables, measurements, and conclusions, nothing more. This direct approach cut weeks from the usual bureaucratic process. Commanders could request technical guidance on Monday and receive a usable specification by Friday. By 1943, the laboratory had expanded beyond its original facilities. Temporary test grounds were set up across Britain to simulate overseas conditions, desert sand, marsh soil, and coastal clay. The aim was to prepare for the eventual Allied return to continental Europe. Glanville knew that success in any large-scale invasion would depend on logistics, not just combat power. Vehicles had to land, move, and resupply without interruption. His engineers were quietly solving the problems that would later define the Normandy campaign. One major breakthrough came with portable roadways and landing surfaces. Traditional concrete runways took weeks to pour and cure. Glanville's group experimented with interlocking steel mesh panels and precast concrete slabs that could be assembled in a day. The Americans developed a similar concept known as PSP, perforated steel planking, and Glanville's earlier experiments provided critical data on load distribution and soil pressure that validated its large-scale use. His laboratory also provided consulting data for pipeline construction, particularly the Pluto project, pipeline under the ocean, which delivered fuel to Allied forces after D-Day. Glanville's experience with soil behavior under stress guided the design of protective casings for sections of pipe laid beneath roads and coastal installations. By the middle of 1943, Glanville's influence extended across nearly every engineering discipline in Britain's war effort. His laboratory's initials, RRL, appeared on thousands of classified documents ranging from bridge manuals to airfield maintenance guides. Despite the scope of his contributions, Glanville himself remained largely anonymous. He rarely appeared in press briefings or official speeches. Within government, however, he was recognized as one of the few individuals capable of translating scientific data into operational capability within days. In one internal memo from the Ministry of Supply that year, a senior official described the Road Research Laboratory as an independent corps of engineers without uniforms. That phrase captured Glanville's philosophy perfectly: civilians applying methodical science with military discipline. The results spoke for themselves. Convoys traveled farther with fewer breakdowns, bridges held under extreme loads, airfields survived record levels of traffic, and shelters built using his blast resistance data saved thousands of lives during later air raids. By the end of 1943, the laboratory had effectively become part of the Allied invasion planning apparatus. Its test results were feeding directly into the designs of temporary harbors, supply depots, and the networks of roads that would connect them. The war had begun as a fight for Britain's survival. Under Glanville's guidance, it was becoming a lesson in applied engineering. How precise measurement and disciplined testing could shape the outcome of a global conflict. And as the invasion of Europe drew closer, the quiet engineer who once studied civilian traffic patterns would soon see his work tested on a scale no scientist could have predicted. 1944, Southern England. The Allied invasion of Europe was no longer a theory. Every military engineer, scientist, and logistician was now focused on a single objective: getting an army across the English Channel and keeping it supplied once it landed. For months, the planning rooms of the War Office were filled with blueprints for bridges, piers, pipelines, and landing strips. Hidden among the names of generals and commanders was one civilian signature that appeared again and again: Sir William Henry Glanville, director of the Road Research Laboratory. Glanville's laboratory had already proved that infrastructure could survive under extreme wartime conditions. But Operation Overlord required something far greater: temporary structures that could perform like permanent ones. The Allies couldn't wait weeks to build ports or roads in occupied France. Everything had to be modular, transportable, and strong enough to handle thousands of tons of vehicles and supplies each day. The Road Research Laboratory's role expanded dramatically in early 1944. Working under the Ministry of Supply and the British Chiefs of Staff Committee, Glanville coordinated with the Engineer-in-Chief of the War Office and several Allied research groups. His team began testing components that would later form part of two of the war's most critical engineering achievements: the Mulberry Harbours and the Allied beach roadways. The Mulberry project aimed to create artificial harbours capable of unloading thousands of tons of cargo onto open beaches. Glanville's lab was assigned to test the stability of roadways and floating platforms that would link the anchored pierheads to the shore. Each section had to bear the repeated loading of trucks, tanks, and artillery without collapsing into the sand. To simulate these conditions, Glanville's engineers built large-scale mock-ups along the southern coast. They tested different mixtures of concrete, steel mesh, and wooden reinforcement, analyzing which combination offered the highest strength-to-weight ratio. They studied tidal forces, wheel abrasion, and the pressure of vehicles braking on gradients. The resulting data determined how the mulberry roads, known as whales and beetles, would be assembled and anchored. Their findings were not glamorous, but they were decisive. The laboratory proved that flexible, jointed steel spans performed better under dynamic loads than rigid concrete ones. That insight directly influenced the final design adopted by the Royal Engineers and American Seabees. Simultaneously, Glanville's laboratory supported the design of temporary landing strips for the Royal Air Force and the U.S. Army Air Forces. As Allied planners anticipated rapid movement inland after D-Day, they needed a system to construct operational airfields within 48 hours of securing territory. The Road Research Laboratory's earlier studies on soil behavior and compaction became the foundation for these advanced landing grounds, ALGs. Glanville's team provided data on the minimum base thickness required for fighter and transport aircraft, depending on soil type. They also supplied material recommendations for square mesh track and Sommerfeld tracking, metal matting systems used to create instant runways. Many of the ALGs in Normandy were built using these exact standards. The results were extraordinary. Within days of the landings, Allied aircraft were operating from freshly built airstrips behind the beaches, providing close air support and supply drops. Glanville's contribution extended beyond field surfaces. His team also studied pipeline safety and road pipeline interactions for the Pluto pipeline under the ocean system. Fuel was the lifeblood of the invasion, and the pipelines feeding it from Britain to France had to cross roads, bridges, and temporary structures without damage. The Road Research Laboratory's stress test determined how deep to bury sections under heavy vehicle routes and how to reinforce them against vibration and shifting loads. Behind the scenes, Glanville's quiet leadership was becoming a model of wartime efficiency. He coordinated not only engineers but also statisticians, metallurgists, and physicists, turning the laboratory into a multidisciplinary hub. Reports were routed to multiple ministries, and information flowed both ways, from theory to application, from field feedback back to research. He maintained an unusual rule. Every experiment must have an operational purpose. If a test couldn't produce a direct improvement in field performance, it was abandoned. That ruthless practicality kept his department focused and relevant, while many others were still chasing theoretical advances. By June 1944, when Allied troops began crossing the Channel, Glanville's fingerprints were on nearly every key structure supporting them. From the steel surfacing under the first tanks landing at Gold Beach, to the bridges and roads used to connect the Mulberry harbours, to the reinforced soil foundations beneath temporary depots and fuel lines. Although few soldiers ever heard his name, his impact was visible in every photo of the Normandy beaches, the steel tracks stretching from water to land, the trucks moving without sinking into sand, the pier roads that kept the supplies flowing even after storms. After the landings, Glanville's team continued to operate at full speed. They received data from military engineers in Normandy and used it to refine their designs for subsequent campaigns. One area of study was the performance of roads built on reclaimed French farmland. The soil, rich in clay, expanded after rainfall and destroyed normal surfacing layers. Within weeks, the laboratory produced new specifications for drainage systems and stabilizing materials that were immediately distributed to the Royal Engineers. By the end of 1944, the success of the invasion had transformed Glanville's laboratory from a national asset into an Allied one. American, Canadian, and British officers all drew from its studies. The United States Army Corps of Engineers incorporated many of its road and runway standards into their own manuals. But Glanville himself remained out of the spotlight. He rarely attended award ceremonies and refused most interviews. For him, the work spoke for itself. The real measure of success was whether soldiers could move faster and safer than before. Inside official records, his contribution was summarized in a single line. Provided essential technical data for the design of transport and field engineering works supporting Operation Overlord. In reality, that meant the difference between chaos and order in one of the largest amphibious operations in history. By the final months of 1944, as Allied forces pushed through France and into Belgium, Glanville's wartime methods were being adapted again, this time to rebuild what the war had destroyed. His focus shifted from temporary infrastructure to permanent reconstruction, a transition that would define his post-war legacy. But before peace returned, his laboratory still had one final mission: to prepare the groundwork, literally, for the recovery of Europe. 1945. The war in Europe was ending. German forces were collapsing, cities lay in ruins, and Europe faced a new kind of battle: reconstruction. Roads, bridges and airfields that had carried armies now needed to carry relief supplies. Millions were displaced, industries were shattered, and every nation faced the same urgent question: how do we rebuild? And who has the knowledge to begin? In Britain, that responsibility fell to a select group of engineers and planners who had spent the past 6 years solving problems most peacetime scientists had never faced. At the center of that group was Sir William Henry Glanville, still directing the Road Research Laboratory under the Department of Scientific and Industrial Research. His laboratory had been crucial to wartime mobility, but its purpose was shifting once again. Glanville's focus turned from temporary survival to permanent resilience. The war had exposed the weaknesses in Britain's infrastructure: inadequate drainage, aging bridges, and materials that decayed under heavy industrial traffic. Now, with access to years of wartime data, Glanville began designing the foundation for a modern transport network. The first step was research consolidation. Throughout the war, hundreds of tests had been conducted under extreme conditions: bridge load data, soil compaction measurements, and blast resistance charts. Glanville ordered them all compiled into comprehensive technical reports. These documents would become reference manuals for Britain's civil engineers, guiding reconstruction for decades. Under his direction, the laboratory expanded its partnerships with universities, local councils, and the Ministry of Transport. Its wartime experience with rapid construction led to new methods for prefabricated bridge assembly, standardized road surfacing, and improved asphalt composition. These advances allowed Britain to rebuild damaged routes quickly, reducing costs and material waste. But Glanville's attention wasn't limited to the United Kingdom. His work extended across Europe through the Allied Commission for Reconstruction, which sought technical guidance for rebuilding infrastructure in liberated countries. British engineers working in France, Belgium, and the Netherlands carried blueprints derived from road research laboratory reports. Many of those designs, optimized for heavy loads and fast construction, were Glanville's legacy from the invasion planning phase. By 1946, his reputation within engineering circles was unmatched. He was appointed director of the Building Research Station, merging two of Britain's most influential scientific institutions under his leadership. The goal was to integrate wartime material science with civilian architecture to make peacetime buildings stronger, safer, and more efficient. In this period, Glanville's teams conducted pioneering studies on road safety, vehicle braking systems, and construction material fatigue. The data formed the basis for new national standards that are still recognizable today. For example, the modern classification of road surfaces by durability and load tolerance traces directly back to the laboratory's work during his tenure. Despite these contributions, Glanville remained largely out of the public eye. He didn't seek recognition or political influence. Most of his work circulated through technical journals and government archives rather than newspapers. Even when he was knighted for his service to engineering and science, few outside professional circles knew the scale of his impact. Yet within those circles, his influence was profound. Engineers who had worked under him described him as meticulous, disciplined and quietly demanding. He emphasized results over rhetoric, insisting that data should always drive design. His leadership style, clear goals, minimal bureaucracy, maximum collaboration, would later inspire how Britain managed its post-war research institutions. In 1952, Glanville became president of the Institution of Civil Engineers, one of the highest honors in his profession. His speeches from that time reveal a recurring theme: the belief that science and engineering were not separate from society, but its backbone. He argued that every advancement in transportation, construction, and materials was ultimately about one thing: stability. A stable road, a stable bridge, a stable nation. Glanville retired from government service in the mid-1950s, but his legacy continued through the institutions he had shaped. The Road Research Laboratory evolved into the Transport and Road Research Laboratory, TRRL, an organization that would later pioneer studies in road safety, vehicle emissions, and traffic flow modeling, all building on foundations Glanville had set decades earlier. Ironically, the very nature of his work ensured his obscurity. His innovations weren't designed to be seen, they were built into the concrete under every runway, the steel of every bridge, and the asphalt of every major road laid in the post-war years. The world moved forward over his work without noticing the name behind it. By the time of his death in 1976, Sir William Henry Glanville's wartime role had faded from public memory. His laboratory's wartime reports remained classified for years, and later generations of engineers inherited his standards without realizing where they came from. But within professional archives, his signature still appears on the blueprints that defined Britain's ability to endure and then to rebuild. He had never led troops, fired weapons, or stood on a battlefield, yet his calculations determined how the war could be fought and how peace could be rebuilt. When historians describe the Second World War as a triumph of logistics and industry, they are describing his world, a war fought not only with courage, but with concrete, steel, and the quiet precision of men like Sir William Glanville. And while the soldiers advanced, it was his roads, bridges, and runways that carried them there. Silent evidence of how one engineer's discipline helped build the path to victory and then to recovery.